Okay, so we're going to isolate the plan when you're trying to calculate the acceleration is pretty much always to isolate both of the objects, all of the objects that are connected. Um, so free body diagram of the whole system. So there's one. There's the other one. There's a weight force acting down. That is 110 kilograms times 9.81. So that's 1079.1. And then the force applied by the ground, that's a force, a pushing force along a flat surface and without friction. And so we know that that is perpendicular to the ground. And we know it's toward the chosen body, away from the contacting body. In other words, it's up. So that is the normal force. And then the last place that there's contact is at the cable. So there's the little stump. And coming out of it is a tension of 250 newtons. So Newton's second law says 250, 0 plus 0n plus 0 negative 1079.1 is equal to zeros. And no, I'm sorry. The other class I'm teaching right now is statics, where there's never any acceleration. So that's just a bad habit from that class. Okay, is equal to the mass, which is 110, times the acceleration. And what do we know about the acceleration? Anything? So if we don't know anything about it, we just enter it as ax, ay, like we don't know either component. But we know that these things are moving along they're moving horizontally because that's the direction of the ground. So we're going to have a in the x component and 0 in the y component. And we're trying to solve for a. And so this gives us, we get two equations. The first one says 250 is equal to 110a. So a is equal to 250 over 110, so positive 2.27 meters per second squared. And the second one, I didn't ask for this in this problem, but it says that negative 1079.1 plus n is equal to 0. So that gives us that n is equal to positive 1079.1 newtons. Oh, and by the way, it can be a little confusing with using n's for normal force and n's for newtons. So I'm always writing my n's for normal force is sort of like a fancy capital N, and my n's for newtons is plain N. So how do we go from this value for the variable to the acceleration vector? That's right. So back in this equation, this is the acceleration vector. We just have to now plug the value for a that we calculated into here. And so you get the acceleration vector is positive 2.27 meters per second squared, 0. Any questions about that? Okay. So now take a few minutes and do part B.